Okay, so we are the Capstone LA team working with Boeing on a project called Operations Data Analysis and Management System. My name is Jesus Mendoza, and my team includes Maximilian Orozco, who was part of the UI front-end team, Richard Balbuena, who is part of the backend server development team, and Nathan Lee, who's part of the graphing and visualizations team. We'd like to really thank our Boeing representatives for working with us throughout the duration of this project. Sen Yao and Ray Hogan have provided so much feedback and input throughout the development of this project, and we really appreciate their support, as well as our academic advisors, Professor Sue Lim and Professor Russ Abbott, who have provided assistance as well. Okay, so let's get started. So let's start off by talking about what ODAS is. So currently there are several hundred satellites in orbit around Earth, which provide us with a lot of functionality, such as GPS location and telecommunications. ODAS is an application that's designed to gather the health and status telemetry produced by these satellites in order to determine whether a satellite is at a potential risk, or as well as performing some initial predictive analysis. So currently there are a lot of C2 systems, which are command and control systems, which allow receiving and sending of telemetry to these satellites. The difference from ODAS is that instead of receiving and sending raw telemetry, ODAS is in charge of handling, manipulating, storing, and analyzing the telemetry that is produced by these satellites. Some of these functionalities include things like predictive analysis using machine learning, as well as storage solutions to manage all these millions of telemetry data points. And lastly, include graphical playback and data visualizations for the data that's being captured. So because ODAS is an all-inclusive application based around a web framework that allows the user to communicate with the backend system that we wrote, we decided to compartmentalize our project as follows. Our front-end application was written with React.js, which is a JavaScript framework, as well as Plotly.js, which is a library that allows us to use data visualizations and graphing capabilities. For our backend application, we use Django and Django REST framework to serve and receive the requests from the front end, as well as a MySQL database to store the relationships between telemetry, satellites, and the millions of telemetry points that are captured. Including that, we have a machine learning application that enabled us to do some initial predictive analysis, and we used Python for that. We developed it using Jupyter Notebook, which is the environment that we worked on, and used several different libraries such as pandas and scikit-learn to develop predictive models. And including that, we also used several remote systems that allowed us to host this application on the internet, such as AWS RDS to host our database, and AWS EC2 to host our virtual private servers. And then we use Docker to containerize our application and improve scalability when deploying. So just to cover the brief overview of the architecture of ODAS, we can see that there are three main components that comprise ODAS, that being the front-end application, the back-end application, and a machine learning implementation. So you can see here in the data flow diagram that the user will always interact with the front-end application, that being the user interface, meaning the buttons and the clicks and everything that has an action, and then the graphing module, which is displayed to the user. So through that user interface, the front end needs to communicate to the back end, and all the requests are authorized, as you can see, through an authorization module, which will allow or deny requests through our backend API. Then, based on the requests provided by the front end, our API grabs the associated data from our database that was either generated by the report generator or the data analysis. And then our API then serves back that data to the user interface or the graphing module, if that's the corresponding data telemetry. Once the front end receives the data back from the API, then it gets delivered and shown to the user. So to talk a little bit more about how the front end application works, I'm going to hand it over to my teammate, Max, to discuss the front end. Max, I believe you're muted. Max, go ahead and unmute. I believe you should have control.
Hello?
Yes.
Sorry about that, my controls disappeared. Okay, hello everyone, my name is Maximilian. My part in this project was to make the other modules look a little easier on the eyes with a clean and simple user interface so that the user can easily access the features in the backend. For the front end, we chose a JavaScript framework called React.js due to its modular code structure, high scalability, and its relatively quick development process. For the design process, I used a couple tools. One is called Adobe XD, which I used for mockups, designing, and to get the spacing, alignment, and placements just right for the elements. I also used a web application called draw.io for the to sort of map out the user experience and the data flow of the program. Now, from the front end, the user is able to sign in with an email and password through a drop-down form that's accessible from any page. Once they sign in or sign out, a toast message is displayed at the bottom right to indicate a successful action. If the user does not already have an account, one can be created from the registration page with a username, email, password, and an optional invitation code. The invitation code will add them to an organization that's associated with satellites and other equipment. Once the user is signed in, they can go to the file upload page where they can choose a file from their file system, add a description, and store it on the server. All of the user's files can be viewed in a dynamic file list that also includes the date, description, and the file name. From the list, the user can also request a data analysis on any given file, download it onto a different computer, or delete it from the server completely. And once the file is successfully uploaded and analyzed, the user can create custom data queries using the dynamic checkboxes and drop-down menus. In addition to the date picker, once the data is retrieved from the backend, it is sent to the graphing module where it is displayed for the user in an easy-to-read manner. Now, to talk more about how the front end interacts with the backend, I'll pass it to Richard.
So our ODAS backend was developed using the Django web framework. This web framework was vital to our project as it gave us access to many features and libraries such as file functionality, token authentication, and login systems. Django also features object relational mapping, which allows us to create, update, delete, and filter our database using Python code rather than SQL code with Python objects that have data fields that directly affect its respective database column. This makes it easier for us to modify our database from within our code without having to worry about maintaining and constantly updating any SQL code. The main way our frontend communicates with the backend is through API endpoints. These API endpoints are accessed through our frontend with queries that retrieve the relevant data that is being requested at the time. This may include data measurements that are needed by the graphing module, users and organizations that are requested by logins or files, or other data that may be requested by the user interface module. All of this is protected by Django's token authentication system, which requires a user to have a valid token to access any data. Users are assigned a token to them, which ties them to things such as files, graphs, and any personal information. This ensures that the correct user is accessing pages or files that should only be available to them. The API endpoints also require token authentication to prevent malicious users from directly trying to access our data through queries. When users sign up, they can sign up as a standalone user, or they can also receive an invite to join an organization. Within an organization, they are allowed to view data, files, and graphs that their organization already has up. And our website is hosted on a remote Linux virtual machine on Amazon Web Services, as well as our database is also hosted on a remote MySQL DB on Amazon Web Services. And as mentioned by Max, the user is allowed to add new files, delete, and download files that are saved to the user's account. And these files are also protected by Django's token authentication so that other users cannot see files that are stored by other users. And these files are also accessed through the front end through a list returned by an API endpoint. And to talk more about the graphing function, I'll pass it on to Nathan Lee.
All right, the graphing module is a subset of the user interface, which was previously described as the front end. Our graphs take complicated, large, written satellite data and make simple, concise visual graphs that are easier to understand for the user. This allows the user to plot telemetry points as a time plot with limits and to also see data values listed below in a tabular chart. So we'll now see how data from the satellites gets transformed into effective graphs for the user interface. So the graphs use APIs from the backend in order to retrieve data from our database, which was discussed earlier. APIs are basically communication protocols to access data from the database. Our APIs consist of specific data points from a particular satellite or a specific number of recent data points from any satellite. The graphing module will accept any API in that format. When an API is fetched or accessed from the program using React, it is received as a JSON object. This object consists of all of our specific data in JSON format. JSON format consists of key value pairs of unique sets of data values of measurements or names in our case. For our data, we specify and separate which data points we wish to use for our graphs from these objects. Based on user input, the program will choose only the specific data sets that the user has requested to see on the graph. For example, CPU and gigahertz. JavaScript Plotly, a visual graphics toolkit, is used in order to properly display our graph. The data is matched based on component and units and is ordered based on the time that the data point was taken. With that, an interval is set for the graph to move through time and also plot the corresponding points. Plotly allows for the user to also scale the graphs, auto-scale, pan, zoom in, zoom out, export the graph to a PNG file, and many other useful functions. The graph is now ready to be displayed in the front-end user interface previously described, and the user can now dynamically interpret and interact with the data. I'll hand it off now to Jesus, who will talk about the machine learning module.
So as mentioned, ODAS includes several different components in our application. As discussed by my other team members, we talked about the front end, the back end, and now I'll talk about the machine learning implementation that we chose. So with the help of our Boeing representatives, we received sample amount of health and status telemetry data. This data came in the format of a CSV file, which had several different features describing the data. These features, these data points came from different components, which included the timestamp and the data value. So as you can see in the image there, there's an example of some of the data points that we received. So towards our approach, because of the limited amount of features that we had, we chose to use feature engineering in order to better describe the data that was provided to us. To do so, we implemented a functionality called sliding window. What sliding window enables us to do is follow a period of time throughout the timeline of the data that was recorded. In this window, we can generate new features, new statistical features that represent how the data has transitioned over that period of time. This allows us to generate new features that can better describe what is occurring in each time frame that was measured. Once we've generated new features, then we can feed this data into classical machine learning algorithms to develop a predictive model to try to generalize the trend that was observed. So just as I mentioned, we did feature engineering and data pre-processing. You can see on the left image that this was the original data that we received, containing the data value, the timestamp, and the component name. After feature engineering, we generated new features that represent the same data value, as well as preserving the time frames. You can see here that for every period of time, in this case 3, 5, and 7, we developed features that reflect the average, the standard deviation, the minimum, the max, and the fluctuation for each of those time frames. This allowed us to generate new features, which we could then use with our classical machine learning algorithms. For those machine learning algorithms, we chose to use random forest regression and support vector regression in order to forecast the forthcoming periods of time based on these features. Although we did not develop a model, predictive model that could accurately generalize the trend, we did come across several different implementation strategies that we followed, as well as deployment strategies that we chose to implement. Despite not making a successful predictive model, we still wanted to ensure that we had the capability and functionality to deploy a model if one were to be deployed, and we wanted to make sure that our project addressed this situation. So as I mentioned, it was important for us to make sure that we knew how to deploy a model in the case that ODAS would actually contain a functioning predictive model. With these options, we came across several different technologies such as AWS SageMaker, which is a functionality provided by Amazon Web Services to deploy predictive models. During our research, we discovered that AWS SageMaker was very restricted since it only allowed you the capability to use in-house algorithms by Amazon and had little functionality to expand. After doing more research, we then found that we can use AWS SageMaker and provide our own scripts to transfer learn the algorithms that were already implemented. But again, this was very restricting since we wanted to incorporate our own algorithms. And the last case that we came across was using AWS EC2 with Docker containers. So by developing our predictive model into a Docker container, we would be able to launch it in a virtual machine and deploy it using endpoints that we built. So this would be similar to deploying our backend application, except rather than having a web server, we would have a server for our machine learning application. So these are some of the options we came across and tried to implement during our machine learning implementation. So as I briefly mentioned about containerization, we chose to containerize ODAS for several different reasons. So containerization in simply means that we separate out the functionality of our application. So one example of doing this, one reason example that doing this would be for consistency. So because our team developed on several different operating systems, for example, I was working on Windows, Max and Richard were working on macOS, and Nathan was working on Linux. It led to several inconsistencies when launching our programs on different platforms. So what containerization allows us to do is normalize the way our application runs. By developing our application inside containers, we can ensure that any system which runs Docker will always run these containers consistently, allowing us to simplify our deployment process as well as integration within our systems. Another benefit to containerization is that it allows us to separate out the concerns of our project. So rather than having the backend depend on a functionality that may have been implemented on the front end, we can completely isolate them and simply enable them to communicate along the network. By enabling them to communicate, we allow them to work independently from each other and rely that each of them is working. Another benefit to this is that as opposed to a traditional based monolithic approach to developing an application, containerization allows us to separate out the parts of the application that require more demand. For example, if ODAS were to receive a high influx of demand for graphing capabilities in our telemetry data, rather than duplicating our entire application, we simply need to duplicate more containers running the front-end application. And that way we can allocate resources more appropriately to meet demand as we grow. So this allows us to simplify the integration with several different environments, as well as deployment into the cloud for scalability when we meet a variety of demand needs. Okay, so because this was the first year that this project was presented, our Boeing representatives, Sen Yao and Ray Hogan, tasked us with developing a system from the ground level. So rather than developing a fully polished application, we were really tasked with developing the groundwork for an application that would enable the future projects to scale and build upon. So you can see this reflected in some of the design choices that we took. So for example, containerization was a big step for us since it allows us to isolate the way that the project is developed as well as how it's going to scale in the future. That being said, there are several things that we feel could be continued to work on throughout the project, of course. First of all, being the predictive analysis. Although we didn't see extremely great results with our predictive model, we did implement a lot of techniques that would have been used and were properly used in order to address the situation. Some of these things that could be solved by using data that was more descriptive, as well as larger quantities of data in order to subset the true proportion of the problem set. Another sense is that our UI implementation, we could be providing more user interaction and feedback whenever some of the tasks are requested to the backend and sent back. Another functionality that could be improved is the graphing capability. So although we included graphing capability to graph the telemetry points in the database, we think we could have included the capability and functionality to plot multiple graphs simultaneously, as well as has a variety of options of how plotting the graph could have come across. For example, should we plot all the data at once or in a time-lapsed manner as we implemented? So these are some of the functionality points that we feel could be addressed in future projects, as well as how we could have improved our implementation. So that concludes this presentation. We want to thank everybody for listening. I think thank our Boeing representatives as well as our advisors for all the help that they provided.
Any questions? Questions?